Alright, in this video we're going to take a look at solving exponential and logarithmic equations, and just brace yourselves because there's no one mold for every question. You kind of have to look at it and inspect it and see what cards you've been dealt, and then go from there to determine what method you will use to solve it. So I'm going to give you several examples, and we're gonna look for strategies on how to solve these equations. So before we do that, I want us to understand that we're going to be converting numbers to other numbers or equivalent numbers with bases. For example, we're going to be taking the number 8 and converting it to 2 cubed in many cases, or 16 into 4 squared. So be prepared for that. And understand that the 2 and 4 are both called the base, and this 2 and 3 are called the exponents. So we just need to understand that as we proceed into these questions. So the first type of question we're going to look at is the two-sided exponential logarithmic equations. And basically you're going to see either an exponent on the left and the right, or you're going to see a logarithm on the left or the right. And the concept behind this is basically if you can get the bases equal to each other, then the exponents are going to be equal to each other. So if the bases aren't equal to each other, then we're going to see if we can convert them to equal bases. So again, when base equals base, then the exponent equals the exponent. Here's an example. 2 equals 2, right? 2 cubed equals 2 cubed. The base equals the base, and the exponent equals the exponent. The base equals the base, the exponent equals the exponent. Makes perfect sense. So when we wrap this up in an equation, it looks a little different. So as we can look at this, we inspect it, we see that the bases are not the same. But can we convert one of these bases to the other? And it's usually the higher number into the lower number, just to give you a heads up. And yes, we can. That 4 can be converted to a 2 squared. And then we can use our properties of exponents. When we have a power raised to another power, we're going to multiply those powers together. So in this case, we're going to be distributing. So I'm going to use those parentheses around the x plus 1 and distribute this 2 and get this right here. So when base equals base, then exponent equals exponent. So now I can just set the exponents equal to each other, and I get a very simple equation that I can now solve. And x is equal to 2. And you can go back in and check this into the original equation and make sure that it's true. It's always a good insurance policy to do that. Again, here's another situation where the bases are not equal, and we notice that 27 could be converted to 3 cubed. And now the bases are equal. So when base is equal to base, then exponent equals exponent. And all we have to do is apply the properties of exponents to combine these two powers. And we're going to get 12x plus 15. And now we can just set the exponents equal to each other and solve this equation. And sometimes your answer will come out as a fraction. And there you go. So again, this is pretty much routine. However, in this case, we don't have exponents, we have logarithms. So we're going to inspect the base of the logarithm. They're the same, so these values should be the same. Okay, so x is simply 5. In a situation like this, where we don't have a base, we know it's understood to be 10, so the bases are equal. And so now we can just set these pieces equal to each other and solve for x. And when we do, we get x equals 12. And we can check that simply by going back into the original problem and substituting in 12 for x. We get 17. And then going to this side and substituting 12 in for x, and we get 17, and there you go. There's the check. Okay, now this is a second type of question. It's a little different. We don't have a two-sided log. We've got a one-sided log. And so in situations like this, you're usually going to rely on the inverse, which is the exponent, to help you solve it. So knowing that this base is 10, if I convert this back now to an exponent by taking the base and setting the exponent, convert it back to the exponential. And again, if you read these steps, we first again need to inspect it, isolate the log. In this case it is isolated. We don't need to use the properties of logarithms to condense it. So we're really fast forward to step 3, and we can rewrite this in exponential form. So when you pretty much inspect it and tell that you can't set this piece equal to anything over here because there's no logarithm, then you basically have to go to a second method, and that is reconverting it back to its other inverse form. And the inverse of a logarithm is an exponent. And now we can just solve this. And we will get the following answer, 3.45. Okay? And again, you can check that answer by plugging that in for this, and you will get that answer. Okay, again, as you can see, this a little different. This log is not isolated because there's the absence of parentheses, and so we are going to actually add 3 to both sides. Just look at that. Yeah, we're going to add 3 to both sides. And now we're ready to convert this to an exponent because there's really not much else we can do. We can't detach this 6 from this x because there's really implied parentheses around this 6x. So the base of this logarithm is 10, and the exponent is -1, and there you go. And we just solve it like a normal equation, and we get our answer. Now, in these next couple of questions or problems, we're going to take a look at the power of parentheses. In this question, there are no parentheses, so this -2x is not a part of this log 5. So we need to isolate the log part. So we're going to add 2x to both sides, and now we can simply divide by 2 and solve for x. Now notice if you try to convert it to an exponent, we get nowhere. We can't really go anywhere with that conversion. So solving this using your calculator, make sure you use parentheses around that 5 if you're going to do this all in one step, because you will not get the right answer if you don't. If you don't use parentheses, you'll get the log of 2.5 instead of the log of 5, all divided by 2. Okay? Now in this case we have parentheses, and so we can't move that 2x because it's a part of the log. So again, when we're kind of at a dead end as to what to do, the steps you should take is to convert it back to its inverse form. And the inverse of a logarithm is an exponent, and so the base of this logarithm is 10, and that's going to give us this, and we know that anything to the 0 power is 1. And we just simply solve this equation. We get x equals 2. Okay, now in this one, we still have a one-sided log. We can't isolate any particular log, but noticing that this is an addition problem, what I'm going to do is use my properties of logarithms to roll it back up into one log. So this 3, before it was in front, was the exponent, and this addition problem implies multiplication. And again, if you're kind of lost at this point, then you need to go back and brush up on the properties of logarithms. And now we're at that point where we just have one log, and we can now convert this to its exponential form. So the base of this log is 10, and 10 cubed is equal to 8x cubed. And you just simply solve it, taking the cube root of both sides. The cube and the cube root cancel each other out, and so we're left with x equals 5. Alright, here's another one where we have to roll it up into one solve. So we're going to put that 2 back on the exponent, Subtraction with logarithms implies division with exponents. And now we can reconvert this now to exponential form and solve it. And we get x equals 2 and negative 2. Anytime you get a negative answer, you want to make sure that you can use it because logarithms can't be negative. All right. Now this is the third type. This is where you have bases where you can't convert them. You can't change a 7 into a 20 or vice versa. So we're going to simply take the log of each side. Golden rule says what you do to one side, you do the other. And we'll use that power property, and we'll take that 3x and cut and paste it out in the front. And now we're solving for x, so we're going to divide everything through by 3 log 7, and on our calculators, using the parentheses wisely, we will divide this out and make sure you get this answer. Here's another one. Now, instead of taking the log of both sides, we could rewrite this as a logarithm and write it as log base 6 of 21 is equal to 2x, and then can we use our change of base formula, which is log 21 over log 6 is equal to 2x, and get a number out of that, this side over here, and divide that number by 2. Or you're going to just notice that log 21 over log 6 for a second. Just keep that in mind. You can take the log of both sides. You're essentially going to get the same thing. You'll see here in a minute. And you'll notice I got log of 21 divided by log of 6. And that 2, remember that 2x was with the other problem, you just divide by 2, which is what we did here. And there's our answer. All right, we're almost done. We're going to do one more. In this case, again, 3 cannot be converted to 101 and vice versa. So we're going to take the log of both sides. In this case, we have x plus 4. We need to wrap that up in parentheses. And when we put it out here in the front, we can't simply just divide by 4 log 3. We have to take this in steps because this is a factor in and of itself. So I'm going to divide by this factor, and then I can subtract 4. And using the calculator, of course, you will calculate that and subtract 4. All right, so that concludes this lesson. We covered quite a bit of material, and this was quite lengthy, so hopefully you got to see several samplings of different types of logarithmic and exponential equations.